Hey everyone, in this video we're going to go over section 2.6, limits at infinity, and how they relate to horizontal asymptotes. By limits at infinity, I'll often say limits to infinity. I mean, we want to see what the behavior of some function of x, how f of x is behaving when we let the value of x increase without bound to positive infinity. Or we can take the limit as x goes off to negative infinity of f of x. And like I said, we want to see what the behavior of f of x is. If we kind of, I always thought of it as you have a wind-up toy and you just set it down the x-axis. What is f of x going to do as that wind-up toy gets really, really far away? So let's start off with an example. Let's start off with, well, f of x being equal to x squared minus 1 divided by x squared plus 1. And so let's talk about what happens as well as we let x get big. In this problem, notice that we're going to square x. So no matter what value of x we plug into f of x, we're going to have f of x be equal to f of negative x. So I'm going to get some values from this function. I'm going to put them in a table. We're going to have an x column and an f of x column. Well, if we plug 0 into f of x, we'd get f of 0 is equal to 0 squared minus 1 divided by 0 squared plus 1, which is negative 1 divided by 1, or negative 1. Let's let x get bigger. Let's see what happens when we say f of 5. Well, we would get 5 squared minus 1 over 5 squared plus 1. This gives us 24 over 26, which equals 13. Which equals 12 divided by 13. So 5, we got 12 divided by 13. Let's keep going bigger. What if we put 10 into this function? Well, that'll give us 10 squared minus 1 divided by 10 squared plus 1. That'll give us 100 minus 1, or 99, divided by 100 plus 1, 101. Notice how these two numbers are getting a lot closer. 99 and 100, their ratio is a lot closer to 1 than 12 and 13 is. If we increase, let's say f of 100. Well, 100 squared is 10,000 minus 1 over 10,000 plus 1, which gives us 4 nines, 9999 all over. Thank you. All over 10,001. And once again, this ratio of 9,999 to 10,001 is a lot closer to 1 than 99 divided by 101. And if we keep this pattern going, as this number increases to positive infinity, this number is going to get closer and closer to 1. It'll never equal 1. If you take a look at this, the only way for this fraction to ever equal 1 is if the numerator and denominator are exactly the same. That's impossible with the way this is set up. But as these numbers get bigger and bigger and bigger, x squared minus 1 and x squared plus 1 their ratio is closer and closer to 1. So for this function, f of x, the limit of f of x as x goes out to infinity, or we could say the limit of x squared minus 1 divided by x squared plus 1 as we let x increase without bound, is going to equal 1. Similarly, like I said at the beginning, we're going to square the value of x. So if we were to plug in negative 5, we would still get a 12 over 13. So I'm going to go through, and for this problem, I can get away with writing a plus or minus in front of these. And as we let x get big, either in a positive direction or a negative direction, the value of x is still going to approach 1. So I can write over here the limit as x increases without bound in a negative direction of x squared minus 1 over x squared plus 1 is also equal to 1. Let me draw a line right there to keep those two separate. And in fact, if we were to draw this function, the function looks kind of like this. It's going to have this line at y is equal to 1 as a horizontal asymptote. We're going to cross, oh, I missed, we're going to, this is our new y-axis. Because it's supposed to be symmetric about the y-axis. That's why I had to go through and correct that. There we go. And we're going to cross at the point 0, negative 1, and at the point on my pen's dying, 1, 0, and negative 1, 0. So, before I keep going, let me go get some more ink in my pen. Okay, sorry about that. So what we had is we had that the limit of this function, that the limit as x approached positive infinity, and it works both in positive and negative infinity, but I'll just talk about positive infinity now, of x squared minus 1 over x squared plus 1. We have a horizontal asymptote at the line y is equal to 1 because this function limits to 1. If we take a limit to positive or negative infinity and it equals a number, that's going to mean that we have a horizontal asymptote at that point. So, we'll combine all that into kind of our intuitive definition of what a limit at infinity is. So our intuitive a limit at infinity. I use the word to a lot. I just feel like at makes it sound like we actually get to infinity, but we never can plug, infinity is not a number. We can't plug infinity into this function. We are just observing a trend in the y values we get from this function as we let the value of x increase without bound. So that's why I don't like to say the word and, I prefer the word to. Intuitive definition of a limit to infinity. So, we'll say let f be a function defined on some interval. Oops. Let f be a function defined on some open interval Now we're going to do, the book gives us two separate definitions. I'm combining them at once on the interval either from a off to positive infinity, or we can have from negative infinity out to some number a, depending on what direction we're going to, either the limit to positive infinity or the limit to negative infinity. So we have a function that is defined on that interval. Then we say that the limit as x approaches negative infinity of f of x, or the limit as x approaches positive infinity of f of x is equal to L if the values of f of x can be made as close to L as we like. So going back to this function, no matter how close, how big of a number we want here, how that's a good way of saying this. So no matter how close we want this number to be equal to 1, we can always come up with some value of x that'll get us there. If we want this function to have some value of 0.99999999999, well, there's going to be a number of x that'll get us there. If I tacked on another 12 zeros, there would also be a number of x. There would also be some value of x, not number of x, I'm sorry. There'd be some value of x that we could plug into this function that would get us there. No matter how close we want this number to be to L, there's always a value of x that'll get us there. That's kind of our intuitive idea. Really, as we like I said, I like to think of it as, instead of us observing what happens to the value of a function as it approaches a point, it's kind of like we got a little robot. And we set that robot down the x-axis forever and ever. And if that robot somewhere out in the infinite ether could shout out what it observed, what had happened in the values of y's as it went on its infinitely long walk, that's what we're getting at. What's happening so far to the right that it isn't meaningful to apply numbers to the x-axis anymore? Limits out to infinity, we're considering values of x is equal to, we can say 10 times 10 to the, oh, and I put 8 zeros there, so that's 10 million. That's a 10 with 10 million zeros on it. We want to know what happens at these incredibly large, both positive or negative. There's nothing sacred about me always going out to positive infinity. Everything would be the same as if I was talking about negative infinity too. But yeah, we want to see what the values of this function, we want to observe the pattern that the values of this function give us as we let x just continue to grow and grow and grow. So one more thing with regards to that. Going back to this definition, intuitive definition of a limit at infinity, and I'm honestly more concerned with you guys' intuitive definition of a limit. If we have the limit of some function of x as x gets really big in either the positive or the negative direction, and if that is equal to some number L, we can say that the line y is equal to L is a horizontal, and there's totally an I in that word, horizontal asymptote of f of x. And I wrote y. I want to say, yeah, if the line y is equal to, yeah, if the limit of f of x as x grows without bound, either in the positive or the negative direction of this function, is equal to a value, then we take that value to be a horizontal asymptote. So, what about if we wanted to, well, let's take the limit, let's consider the function f of x is equal to the tan inverse, or the arctan, the tan inverse of x. And now let's draw this thing. Tan inverse goes off like this. And we have, sorry, I gotta turn my paper sideways. We have these lines like this, with this being pi halves and this being negative pi halves as y values. And this goes out to positive infinity and negative infinity. These are y equals, y equals. So from the graph of tan inverse of x, we can see that the limit as x gets really big in the positive direction of the tan inverse of x, well, as we keep on letting this value get larger and larger and larger, because the range of tangent is every real number from negative infinity to infinity, so the inverse of tangent will accept as an argument every number from negative infinity to positive infinity, and it'll only return values between negative pi halves and pi halves. As we're letting x get big, this function is going to limit to pi halves. Now, you can never plug pi halves into tangent because that would give you the sine of pi halves divided by the cosine of pi halves, which would be evaluated to 1 divided by 0. But we can say that the pattern in these y values limit towards pi halves as we let the value of x increase without bound. Similarly, but the opposite is true in the other direction, if we consider the behavior of the tan inverse of x as we let x get really big in the negative direction, well, this function is going to limit to a negative pi halves. And that's why we have these horizontal asymptotes on the graph of f of x. This is also talking about an overall trend as we get far away. I didn't see this in the book, but I do want to let you know that if we have a function can cross its horizontal asymptote. There is nothing wrong with it crossing a horizontal asymptote. The key word is a finite number of times. It can't oscillate forever like sine of x or cosine of x does about the x-axis. But if we have a function that oscillates once or twice and eventually settles down and then approaches a value, that's fine. We are talking about end behavior. We are talking about, for lack of better terms, obnoxiously large values of x. So if we cross the horizontal, like I said, we can cross the horizontal asymptotes a couple times because we are concerned with this infinitely long pattern, not necessarily what happens in a local part of the graph, but these overall trends. Cool. So let's do our first example. We want to find the infinite limits, we want to find the limits at infinity, and we want to find the asymptotes for this function f, which I forgot to label as f. So remember, limits, infinite limits. An infinite limit is when we get a limit as x approaches some number of some function of x and it equals infinity. This is our infinite limits. Our limits at infinity. Those are our limits that go to plus or minus infinity. They hopefully equal some value of L. So, first off, find the infinite limit. So, notice how I said A. This could also be, we could also have A from the left, or we could have A from the right. Any limit that tends to either positive or negative infinity are infinite limits. So right here, we can see this function, that the limit as x approaches 1 to negative 3, as x approaches negative 3 from the left of this function f, dives down to negative infinity. But the limit as x approaches negative 3 from the right of this function of x, as we approach from the right, it increases to positive infinity. However, we combine these two, the limit as x just approaches negative 3 of f of x does not exist. But that's different when we approach 0. The limit as x approaches 0 of f of x, well, as we approach from the left, it goes up to positive infinity, and as we approach from the right, it goes up to positive infinity. So the limit as x approaches 0 of that function is equal to positive infinity, because the limit from the left agreed with the limit from the right. So those are the infinite limits. The limits at infinity, there's only ever going to be two. If they exist, we've got the limit as x goes off to negative infinity of f of x. Well, if we look at this graph, as this function bends and curves off to the left, the y values are going to approach negative 1. This function is going to limit to negative 1. here is something I would like to say, that you guys technically don't have enough information to know that this thing doesn't spike up over here. If you see a graph, your graphs are going to be self-contained. They're not going to have any mysterious hidden things over here that you have to account for. Anything mysterious over here you have to account for. If you're asked to analyze a graph, your graph is self-contained. So, as x goes off to negative infinity, the values of y approach -1. However, the limit as x goes off to positive infinity of f of x, as our x's increase with that bound, our y values approach a +2. So, our limits at infinity or our limits to infinity are done. But now take a look at what we have. We've got this limit as x goes off to negative infinity equaling -1. So we know we'll have a horizontal asymptote along the line y is equal to -1. And we know we'll have another horizontal asymptote along the line y is equal to 2. We also know that our limits to infinity give us information about our vertical asymptotes. And since we had an infinite limit when x approached -3, we know we'll have a vertical asymptote along the line x is equal to -3. And we'll have another vertical asymptote along the line x is equal to 0. So, all of that together, the takeaway is if we have some limit as x approaches a value of a, or we can take the limit as x approaches a from the left, or the limit as x approaches a from the right of some function of x. And if that limit tends to either positive or negative infinity, then you know you're going to have a vertical asymptote at x is equal to a. If we have a limit as x approaches either positive or negative infinity of some function, and if that is equal to some number, then that tells us that we have a horizontal asymptote at y is equal to L. So, we're going to ask you guys a lot about horizontal asymptotes and vertical asymptotes. That's trying to get you guys to make this connection that limits and asymptotes are directly related. Okay, so we'll build up to a theorem by observing what happens as we let x, let's let x go out to positive infinity of 1 over x. Now our denominator is going to grow without bound. So I'm going to write a pattern in these y values. We can have, well, let's call f of x 1 over x. We'll have an x and a f of x column. We plug in 1, well 1 over 1 is equal to 1. We plug in 10, 1 over 10 is a tenth, or 0.1. If we plug in 100, we get 1/100th, which is equal to 0.01. Plug in 1,000, 1/1000th, and we get 0.001. If I plug in some number with 1, 2, 3, 4, 5, 6, if I plug in 1 million, that's going to be 1 over 1 million, or a 0 with 5 zeros followed by a 1. So as this number gets bigger and bigger and bigger, as the value of x increases without bound, the value of 1 over x is going to tend towards 0. So that's a big takeaway. If the denominator increases without bound, the value of the ratio tends to 0. Provided that the numerator also isn't increasing or decreasing without bound. We'll see some examples here in a bit how we've got x's in the numerator and the denominator. We'll have to tackle those a little bit differently. But for now, simple ratios like 1 over x. As the denominator gets big, the fraction as a whole goes to 0. In fact, any number we put in the numerator, we could put 5 in the numerator. As we let x get big without bound, 5 divided by x will still tend towards 0. Putting all that in a theorem, the book's going to kind of rapid fire us 2 theorems. Let's say if we've got some value of r and it's a positive number. If r is a rational number, and remember a rational number is a fraction, is anything a over b. So if r is a positive fraction, then the limit as x goes off to 0 of 1 over x to the r is equal to 0. Yeah. Perfect, because we're I wrote 0, I'm sorry. Let's say that again. So we have this positive fraction. R is a rational number. And if you guys don't remember what a rational number is just a fraction. If r is a rational number, and we take the limit of 1 over x to the r as r increases without bound, that is going to limit to 0. Now, our second theorem, which really just takes care of limits going in the other direction. We need to be careful so we don't accidentally take a square root of a negative number. Our other theorem is also if r is a positive rational number, and x to the r is defined for all x, then the limit as x goes off to negative infinity of 1 over x to the r is equal to 0. So this is you want to be careful with this, because we can definitely take the limit as x goes off to positive infinity of 1 over x to the 1/2. We can take the square root, the limit as x goes off to infinity of the square root of x, and that's fine because x is always going to be a positive number, or at least x is going to tend to be a positive number when we're considering what happens as x increases to infinity. So we can take the square root of x. Over here, we can't take the limit as x approaches negative infinity of 1 over the square root of x, because the square root of a negative number isn't defined. So that's what we're getting at with these 2 theorems, and why this one talks about being well defined. So we're going to use this new theorem, our 2-part theorem, and we're going to solve some problems. This is going to be kind of our standard approach or standard issue for solving these kinds of limit problems. So let's solve the limit as x increases without bound of 3x squared minus x minus 2 divided by 5x squared plus 4x plus 1. So these problems we're going to multiply this ratio, because if we tried to directly plug this in, we would get an infinity minus infinity minus infinity, and an infinity minus 2, and an infinity plus 1. Doesn't really give us too much meaningful information. But look at what the degree of the denominator is. The degree of the denominator is 2. It's degree 2 because we've got this x squared term. So because it's degree 2, what we want to do is we want to take this ratio and we want to multiply top and bottom by 1 over x squared. What we do to the top, we do to the bottom. 1 over x squared. And this is the degree of the denominator. Coincidentally, in this problem, it's the same. The degree of the numerator is equal to the degree of the denominator. That's why I'm stressing that we're really getting that 2 from the denominator. Coincidentally, they're the same. So let's work that bit out. We'll be taking the limit as x increases without bound. And now I'm just gonna combine them. We're gonna get a 3x squared minus x minus 2 divided by an x squared. And you need these parentheses because that fraction is our numerator. And this fraction, 5x squared plus 4x plus 1 divided by x squared, is our denominator. Now, doesn't that look wonderful? So, we want to simplify this thing. Seems like we took a step in the wrong direction. We made it more complicated. Let's simplify this thing. Well, 3x squared divided by x squared simplifies to 3. Negative x divided by x squared is equal to minus 1 over x. And then we have a minus 2 over x squared. Minus 2 over x squared. In our denominator, we have 5x squared divided by x squared, which gives us a 5. We have a 4x divided by x squared, which gives us a plus 4 over x. And we have a plus 1 over x squared. Do you guys see what I did? How did I, not that part, what did I mess up? What did I forget? I told you, and I really do stress it, you need to write the limit at every step. Because this limit is not equal to this function. The limit of this function is equal to the limit of this function. And I know my limit is kind of floating off. We're using our imagination, and it's right there. Okay, so this is the power of our theorem. As we let x increase without bound, I'm going to write this over here. We're just going to copy the limit as x approaches infinity of 3 minus 1 over x minus 2 over x squared divided by 5 plus 4 over x plus 1 over x squared. So right here, and let me grab our theorem, which I think is on the back half. The theorem says that if we have this rational number r and a limit going out to positive infinity, well, we've got a limit going out to positive infinity, and right here, for this fraction, we have r being equal to 1. 1 is a rational number, so we can apply our theorem. The limit as x goes to infinity of 1 over x to the r equals 0. So that means this limit is equal to, we can ignore the constant 3 in the numerator, the limit as x goes off to infinity of 1 over x is equal to 0, and the limit as x goes off to infinity of negative 2 over x is also going to be equal to 0. We have this, and I know we have a 1 over r here. You can think of 2 over x squared as 2 times the limit of 1 over x squared. Our denominator increases without bound, so the value of that fraction goes to 0. Similarly, in the denominator, this 5 kind of avoids the impact of x going off to infinity. We'll have plus 4 divided by x as x gets really big tends to 0, plus 1 over x squared as x gets really big tends to 0. So the value of this function the value of this limit is equal to 3/5. What does that also mean? Going back to what we said earlier, that means this function, this rational function, f of x, which is equal to 3x squared minus x minus 2, divided by 5x squared plus 4x plus 1, has a horizontal asymptote along the line y is equal to infinity. So, the big takeaway, our technique I wanted to show you is we started off here, and we looked at what the degree of the denominator was. The degree of the denominator was 2, so we multiplied top and bottom of our original rational function by 1 over x squared. That 2 is because of that 2. If it was degree 3, we'd multiply top and bottom by 1 over x cubed. We multiplied by 1 over x squared, we made this beautiful fraction, we simplified. We do this to try and use that theorem as much as we can. We try and get as many x's in the denominator as we can. Why couldn't we just deal with an infinity divided by infinity? I'm going to give you a list of odd results from limits is a good way of saying it. I'll give you a list of odd results from limits here in a couple examples. Once we get into chapter 3 and chapter 4, we can discuss them in greater detail, why they need to be avoided like the plague. For now, I'll just give you a list and know that I'll tell you more about it in the future. Okay, so let's, sorry, I had to check to make sure the camera was recording. Some more limits. Let's consider the function. This will be example 4. Let's consider the function f of x being equal to the square root of 2x squared plus 1, all divided by 3x minus 5. And what we want to do for this problem is we're going to find the horizontal and vertical asymptotes. Find the horizontal and vertical asymptotes. Remember, horizontal asymptotes involve limits going off to positive or negative infinity, and vertical asymptotes involve a limit that is equal to positive or negative infinity. So where the infinity is jumps. So let's find our vertical asymptotes first. Remember, our vertical asymptotes are going to occur where our denominator goes to 0. So that means we know that the limit as x approaches 5/3 of f of x is going to go off to, and we got to figure out if it's going to go off to positive or negative infinity. Let's explore that. Well, the limit as x approaches 5/3, we'll say from the left, of the square root of 2x squared plus 1 over 3x minus 5. So as x approaches as x approaches 5/3 from the left, it's taking on values that are smaller than 5/3. So it could take on, say, 1.5, 1.6, 1.65, 1.66, etc., etc. But it's always going to give us a positive value. So we're going to square it, it's going to give us a positive value. We're going to multiply it by 2, which is positive, and then we're going to add 1 to it. So this numerator is always going to be positive. No matter what value of x, the numerator is always positive. Yeah, always positive. Now, the denominator, when x is less than 5/3, this is actually going to be a negative number. And the closer and closer and closer it gets to 5/3, the more and more negative it's going to get. So we've got a positive number divided by something that's always negative, and it tends to an infinity. That means it has to tend to a negative infinity. Same thing, but the opposite in the other direction. We take this limit as x approaches 5/3 thirds from the right of the square root of 2x squared plus 1, all divided by 3x minus 5. Once again, numerator is always going to be positive. And all the values that we're going to plug in for x are going to be bigger than 5/3, so this denominator is always going to be positive. If the numerator is always positive and the denominator is always positive, and we know that this function has to tend towards either a positive or a negative infinity, well, positive divided by positive means that we'll tend towards a positive infinity. So it's a good thing I stopped when I did over here, because we got to remember to take limits as they approach a value from the left and from the right, because just the overall limit of this function as x approaches 5/3 with the square root of 2x squared plus 1 over 3x minus 5 does not exist. But it's fine, because these were enough. Honestly, one of them was enough, but I'm teaching you, I'm trying to show you everything. If you get one of them, that was enough to know that there was a vertical asymptote at x is equal to 5/3. It's good to go. We did them all. So, horizontal asymptote, that's going to occur at the point x is equal to 5/3. For vertical, our vertical asymptote, vertical is going to be at x is equal to 5/3. It's funny because that's a vertical line. Still wrote it there. Horizontal asymptotes. We've got to take limits as they go out to positive or negative infinity. So let's see that technique we did again. We want to take the limit as x goes off to positive infinity of the square root of 2x squared plus 1, all divided by, I lost it, 3x minus 5. So once again, we observe, we look at what is the degree of the denominator. Well, the degree of the denominator is 1. Degree of denominator is 1. So that means we're going to take this fraction and we're going to multiply top and bottom by 1 over x. 1 over x. Okay? Now, we've got to actually do this algebra. So, this will be, and I'll start down here, the limit as x approaches infinity of, we get the square root of 2x squared plus 1 divided by an x all over 3x minus 5 over an x. So, we're going to use a couple properties of real numbers. X is positive, so we can replace x with the square root of x squared. And we know that the square root of a divided by the square root of b is equal to the square root of a divided by b. We'll use both of these over here to rewrite this as, and I don't want to crowd myself, so we'll go down here. The limit as x approaches infinity. So we're going to replace this x with the square root of x squared. Square root of 2x squared plus 1 divided by the square root of x squared. All divided by, and you need these parentheses. And we'll do the same thing as we did before. 3x divided by x gives us 3, and then minus 5 divided by x. So this denominator, we're going to leave it alone. We just need to not forget about it. We'll still manipulate the numerator a little bit. This is equal to the limit, because it's equal to a limit. These two limits are equal. X going off to infinity of, now we'll apply this rule for real numbers. We get the square root of 2x squared plus 1 all over x squared. Still divided by 3 minus 5 on x. Now we simplify. Limit, x goes off to infinity. We get the square root of 2x squared divided by x squared is 2 plus 1 over x squared divided by 3 minus 5 over x. Okay, the book would go on to show us several more steps. The book would then show us how we're going to split this limit up into the numerator and the denominator. The book would then move the limit into the radical distributed across addition and subtraction respectively, and then evaluate. At this point, once you go to evaluate this limit, I say that you can cross out the 1 over x squared because that's going to reduce to 0. Similarly with the negative 5 over x, that's going to reduce to 0. So what is left over after we evaluate this limit is the square root of 2 plus 0, or the square root of 2, divided by 3 take away 0, or 3. Square root of 2 divided by 3. So it's typically the algebra that is difficult in a calculus class. The concept of limits is definite. It's probably new to you guys, and I don't expect anyone to get it the first time they ever see it. I didn't when I first saw it, but it's this sort of algebra that you guys are going to have to get used to. We're multiplying top and bottom by 1 over x to the degree of the denominator, specifically the denominator. We had a linear term in the denominator, 3x minus 5, so its degree was 1. Multiplied top and bottom by 1 over x and 1 over x. Then we wanted to get this. Why did I do this? Because we wanted to be able to do what we did, how we simplified at this step. We went from 2x squared plus 1 over x squared, and we got to 2 plus 1 over x squared. We wanted to do this sort of simplification. So that's why we wrote x as the square root of x squared, because we knew that we could combine square roots with that rule. So that allowed us to gain access to that numerator. You're looking at the denominator to find the tool you're going to use to manipulate the numerator, if that makes sense. I just realized as I stood up and flipped the page over, we were tasked to do something. We were tasked to find the horizontal and vertical asymptotes, and I just kind of trailed off after finding a number. So let's finish what this problem asked us. To find those horizontal asymptotes, we took a limit that went out to positive infinity, and it was equal to the negative square root of 2 over 3. That tells us we have a horizontal asymptote along the line y is equal to square root of 2 over 3. Now, what our theorem says is that we also need to go back to negative infinity, and for that 1 over x to the r, we needed this to be defined for all values of x. And if you look, if we were to go through, and let's get some more paper, we wanted to take the limit, and I am going to jump back at this point. The limit, because all of our algebra is going to be the same, I just want to illustrate a point. So we know this is defined because no matter what value of x we plug in, we're going to eventually square it, which is going to force this to become a positive number. And as we let x get really big, this is going to get really close to 0. So we're never at risk of taking the square root of a negative number. Down here, we're going to 0, but there's not a positive or a negative 0 like there's a positive or negative infinity. We just tend towards 0. So we're still going to get the square root of 2 over 3. Unlike the previous examples, this function, wherever I choose to point, that function only has one horizontal asymptote, kind of like the very first example with x squared minus 1 over x plus 1. So I want to jump ahead to something that the book doesn't present until later into this section, later in this chapter, in all honesty, but we have experienced it once before and we're about to experience it again. We will call these things indeterminate forms. Indeterminate forms. Because we can't determine the value of anything of the form, say 0 divided by 0, infinity divided by infinity, 0 times infinity, and these are bullets, and that's the multiplication dot. infinity minus infinity, 0 to the 0, 1 to the infinity, or infinity to the 0. We've got, I believe, 7 of them. 1, 2, 3, 4, 5, 6, 7. Perfect. So we have those 7 indeterminate forms. If you go to evaluate a limit, the first thing you want to do is see if you can just plug in the value of a limit. If that doesn't work, it might be because you ran into one of these indeterminate forms. That's why, and I already put it down. That's why in this problem that we first did, if we tried to just see what happens, that's why I said we get this infinity minus 2 for infinity plus 1. And the infinity minus infinity, we don't really, our human minds just can't grapple with what that means, and infinity divided by infinity kind of falls in the same boat. That's why we went through into this algebraic manipulation. So, why am I telling you this? Limits, I'll say this, I would always encourage you guys to take the path of least resistance. Unless you're just trying to develop a skill. Then take the path of most resistance. If you're trying to solve limits and you run into one of these, we've already seen an example of this, and our next is going to be an example of that. You're going to have to come up with a way to algebraically manipulate the problems like we have been. Once again, this example would give us an infinity divided by infinity 2, which is why we went through this sort of acrobatics to get out of that situation. If you get one of these, and it is, if you don't have to memorize them now, but at least be aware that there are 7 indeterminate forms, and it will help you in the future to at least be able to recognize these. If you run into one of these indeterminate forms when you're solving a limit, you're going to have to go through some algebraic sort of acrobatics, as I said, to get out of that indeterminate form. So let's go back to over here. So let's talk about the limit as x goes off to positive infinity of the square root of x squared plus 1 minus x. And if we were to try and immediately directly solve or plug this bound in, well, as x increases without bound, x squared plus 1 square rooted is going to increase without bound. This will tend to an infinity. Similarly, as x increases without bound, x increases without bound. So that too tends to an infinity. And infinity minus infinity is one of our indeterminate forms. Infinity is more of an argument about size, and there's no way to compare relative sizes of these infinities. There are different sizes of infinities, but that is definitely not a topic for today. For now, we don't know which one of these is bigger. We're just saying this is more of a concept. How do you remove a concept from a concept? So we just kind of struggle with this as a species to deal with. So it is our duty, it is our goal, it is our privilege and our joy to manipulate this function in such a way that this limit becomes easier to evaluate. And I want to demonstrate the technique. If you get an infinity minus infinity, especially if you have a square root, what they say is you want to multiply by the conjugate radical. I had to find that in my notes. The conjugate radical. So we would multiply top and bottom by the square root of x squared plus 1 plus x divided by the square root of x squared plus 1 plus x. Top and bottom. And x squared plus 1 minus x, you can think of it as having a denominator of 1. And now the reason why we do this, in order to do this, we're actually going to clear out the square roots from the numerator. Square roots are kind of difficult to work with. This is going to be equal to the limit as x goes off to infinity. X squared plus 1 times x squared plus 1 is going to give us, the square root of x squared plus 1 times the square root of x squared plus 1 becomes just an x squared plus 1. We can go plus x times the square root of x plus 1 minus x times the square root of x plus 1. Those are going to cancel each other out. and we'll get minus x squared. Now in our denominator, we just have 1 times x squared plus 1 plus x. The square root of x squared plus 1 plus x. These square roots these x squareds are going to cancel, and we're left with the limit as x goes off to infinity of 1 over the square root of x squared plus 1 plus x. Now, it might not look like much, but we can solve this problem. This is all we need. As x increases without bound, and I don't want to say equals, but I will kind of draw a squiggle arrow, which provides me much more flexibility to write what I'm about to write. 1 over infinity plus an infinity, you can think of it as, like it tends towards this. We couldn't take away infinity from infinity because we didn't know which one is bigger, is one smaller, is it meaningful to even talk about sizes in this case. But if you take something that's infinitely big and you add infinitely more stuff to it, you still get something that's infinitely big. And 1 divided by something that's infinitely big says that this limit is equal to 0. Our denominator grew without bound, so that means this original function, the square root of x squared plus 1 minus x, tends towards 0 as we let x get really big, which hopefully should start to make sense. As we let x get really big, and I mean, what if x is 1 times 10 to the 1 millionth? We have 30 zeros after a 1. That plus 1 isn't going to add much value to it. These two values get really close, the value as x gets bigger. We'll unlock some more skills, some techniques later that'll allow us to analyze growth rates of functions. But for now, we tried to evaluate this limit, and this was example 5. Tried to evaluate this limit, got an infinity minus infinity. That's one of our indeterminate forms. For now, we just know that these need to be avoided. So we tried to multiply by the conjugate radical. We went from a minus sign up and over to a plus sign. We did some algebra, and then we were able to apply our rule. Typically, the way I show work is I would, instead of doing squiggle arrow, I like up diagonal arrow. At some point, you just have to show me how you're evaluating your limit. I'm really looking forward to work for your calculus when you go from the stage where you write limit to the stage where you don't write limit. Obviously, you have to do that part correct too, but I'm concerned with your calculus. Okay. So, these indeterminate forms. I'm a teacher. I feel compelled to tell you I'm going to erase the whiteboard if you haven't copied these down yet. Now's your last chance, or you can pause the video and go back a minute. Recognize your indeterminate forms. There's 7 of them. See if by the time we get to chapter 3 you can remember them all. Example 6. This is starting to deal with substitutions. You guys have a lot of flexibility in your approach to calculus problems. There's never one approach to solving a math problem. Now there are more apparent approaches, I would say that. Typically the problems are geared so that there's one approach. Now there's a lot of different ways you can think of a problem. Like if we took the limit as x approaches 2 from the right, of the arctan of 1 over x minus 2. And arctan is just a tan inverse of x. Potato, potato. So, look at what happens as we let x increase. X is getting closer to 2 from the right. So it's taking on values like 2.1, 2.01, 2.001. The value of x is always going to be greater than 2. It's going to get really close to 2, but it's always going to be greater. Well, that means this inside argument is always positive. And as that denominator gets smaller and smaller and smaller, this number as a whole is going to shoot up towards positive infinity. So we can actually say that the limit as x goes off to 2 from the right of the arctan of 1 over x minus 2 is equal to the limit. And I'm going to come up with some new variable. I'm going to pick t. I chose t because the book chose t. As t. And so as 2 went off to infinity, 1 over x minus 2 went off to positive infinity. We're going to replace this with a positive infinity. And now, talk about the arctan of t. Now, if you remember, as we let t increase without bound, I drew the picture a while ago. I think it was on the first piece. You guys go back in your notes. You guys go back in the video. You go back in my notes. I drew the tan inverse of x for you at one point. I drew it a lot nicer than I'm going to draw it now. So we went off to pi halves and negative pi halves. Okay, so the limit as x went off to 2 from the right of the arctan of 1 over x minus 2, well, that inside argument went to positive infinity, so we simplified this limit and said, well, instead of the arctan of this, well, that's the same. These limits are equal as the limit as t goes off to infinity. Well, you can think of this as our t-axis. Really, as the inside argument of arctan increases without bound, what does the value of arctan do? Well, the value of arctan approaches pi halves. So this limit is equal to pi halves. This was trying to show you how we can do these limit substitutions. You can directly go from here to pi halves. There's nothing wrong with this. Is kind of like showing your work, showing in between steps. I'm teaching, I'm demonstrating this to you guys, so I really try and show every single step, especially since you guys aren't sitting in front, behind me, wherever, able to ask questions on the fly, so I'm showing everything. Like I said, also, you don't have to do these substitutions. If you can jump from here to here, that's fine. But know that you can do limit substitutions, because the arctan of 1 over x minus 2 is not the same as the arctan of t, but the limit as x approaches 2 from the right of arctan of 1 over x minus 2 is equal to the limit as t approaches infinity of the arctan of t. That's what we're saying with this equal sign right here, that these two limits are equal. So another example of that substitution. In order to do this one, we're going to talk about the function f of x is equal to e to the x. And we want to make an observation. You can't calculate this by hand, so there's no point in hiding it from you. This was pretty shamelessly stolen out of our book. So the value of e to the x, and I hope you guys can read this, the value of e to the x gets really closer to 0 as the value of x gets more and more negative. In case this is too small for you guys to read, grab your calculator. E to the 0 should be equal to 1. See what e to the negative 1 is. E to the negative 2, negative 3, negative 5, negative 8, and negative 10. By the time we get to negative 3, we're already at about 0.05, and at negative 10 we are at, honestly, about 0.123, So as x gets really small, e to the x approaches 0. E is about 2.7. So it'll never go negative. It'll never go less than 0, because the only way to multiply a bunch of stuff together and get a negative number is if an odd number of those things you multiply together were negative. So e to the x approaches 0 as x gets closer to negative infinity. So an example of these limits, that means, or the substitution with regards to limits, is we can say things like the limit as x approaches 0 from the left of e to the 1 over x. Well, the limit as x approaches 0 from the left of e to 1 over x. 1 over x as x gets really small, as the denominator gets smaller and smaller, the number as a whole is going to get bigger and bigger and bigger. But since we're approaching from the left, all of our numbers are going to be negative. So we're going to get big in a negative direction. So this limit is the same as the limit. We chose t last time. I assume you guys are going off towards some STEM major or taking this class for fun, so we'll introduce a Greek letter, lambda, as lambda goes off to negative infinity of e to the lambda. Well, as the value of the exponent decreases without bound, the value of e to x tends to 0. So once again, we're just doing limit substitutions here. I threw a lambda in there just to get you guys used to seeing more Greek. Like I said, you don't always have to go through. If you in your mind can go, cool, so this becomes e to the negative infinity, and that's going to tend to 0. I'm okay with you guys making that jump. This is a good in-between step, and the real why this is equal to that. So we're getting kind of close to the end. Let's... Can I run on the back? No, we'll save a treat for now. So I said earlier, I'll say again, limits as x go out to, honestly, positive or negative infinity of the sign of x do not exist. Similarly, limits as x go off to plus or negative infinity of the cosine of x do not exist because they oscillate forever. Sine starts at 0 and goes up and down and up and down, and it forever bounces between a positive 1 and a negative 1. It never settles down. It oscillates forever. The limit of cosine does the same thing, it's just a phase shift away. And for some reason, much harder to draw usually. For the same reason, oscillates between positive 1 and negative 1, never settles down. So these limits do not exist as x increases without bound. So we've got infinite limits, we've got limits at or to infinity. We can have an infinite limit at infinity. If you consider the behavior of x cubed as we let x increase without bound, graphically, x cubed kind of looks like this. It doesn't have a vertical asymptote. It's a polynomial. It's defined everywhere. But as the value of x increases, the value of y increases fairly rapidly. So we can have a limit, a limit at infinity being equal to an infinite limit. That's just saying that as x increases without bound, x cubed increases without bound. And if we let x increase without bound, but in a negative direction of x cubed, well, that'll give us a negative infinity. We dive down towards negative infinity. So we can have limits at infinity, at positive infinity, at negative infinity, and those limits can tend towards positive or negative infinity. Those limits might not exist, or those limits could be equal to a number. Just like with the limit going to a nice letter A, how it can equal a number, it can go to positive infinity, it can go negative infinity, it cannot exist. Same thing applies for infinite limits. Kind of going back to our indeterminate form, this example honestly should be about 4 examples ago. Example 10, taking the limit as x goes off to infinity of x squared minus x. These parentheses are technically pretty important, there's nothing pretty about it. I wrote it. You guys have been forced to read my handwriting, for which I apologize. But without it, just kind of splitting hairs, the limit as x goes off to infinity of x squared minus x. Without parentheses, this is technically the limit as x goes off to infinity of x squared. That whole thing minus an x. You need parentheses to say that we're taking the limit of this whole, well, it'd be a binomial, of this whole polynomial, as compared to the limit of this term, and then we'll subtract a value of x. Splitting hairs, but you need it. So, also, like I said, limits are easy when we can just directly evaluate them. So we try and directly evaluate this, and we get an infinity minus an infinity. That's one of our indeterminate forms. One of our 7. I had them written down again. Here's our 7 indeterminate forms again. 0 divided by 0, infinity divided by infinity, 0 times infinity, infinity minus infinity, 0 to the 0, 1 to the infinity, or infinity to the 0. We try to directly solve this limit, we get one of our indeterminate forms. That leads us to an infinity minus infinity. We scratch our heads, we go, that doesn't make any sense. Let's try something else. So far, these are the only 7 things that we really need to avoid. And kind of like how the argument of you can take something that's infinitely large and add an infinite number of stuff to it, and you still have something that's infinitely large. Oops, as x goes off to infinity. Let's factor an x out. Well, as x grows without bound, this is going to tend towards an infinity times an infinity, which is fine. We can deal with an infinity times an infinity with the same logic that we deal with an infinity plus infinity. You can think of infinity by infinity as a geometric problem. If you have a square whose base is infinity units long and whose height is infinity units tall, well, that means you're going to have an infinite number of square units in the middle. So infinity times infinity is fine. We say this limit tends to positive infinity. So, like I said, be cautious. These are the 7 indeterminate forms. And when we get into chapter 3, taking derivatives, we're gonna experience these a little bit more. L'Hopital's rule is when it's gonna come back. So, infinity times infinity is equal to an infinity. If you get one of our indeterminate forms, see if you can manipulate your problem algebraically and then reassess your limit and see if you got away from your indeterminate form. Okay. Getting close. 2 more limits. Example 11 is if, let's say we wanted to take the limit as x goes off to infinity of x squared plus x all over 3 minus x. This is a lot like what we were doing at the very beginning. This kind of goes back to our standard issue approach for solving these kinds of problems. We are first going to observe, notice, take a look at what the degree of the denominator is. If you look, the degree of the denominator, the deg of our denom, is 1. So, because the degree of our denominator is 1, what we want to do, well, before, the reason why I'm going through this hassle is because when I try and directly plug, see what happens when we go, if we can just directly evaluate this limit, infinity plus infinity, that's fine. That numerator tends towards a positive infinity. But down here, we're going to divide by a negative infinity. And infinity divided by infinity is one of our indeterminate forms. It's not explicitly written, but infinity divided by negative infinity, or even negative infinity divided by a positive infinity. All 3 of these are our indeterminate forms. You can't divide infinity by infinity. So we go through and we do our standard issue approach. We observe what the degree of the denominator is, and it's 1. So we'll take this limit. X gets super big. X squared plus x divided by 3 minus x. We're going to multiply top and bottom. 1 over x. 1 over x. And now we're going to perform this multiplication. That'll give us, or this limit is equal to, the limit as x approaches infinity of x squared divided by, or x squared plus x all over x divided by 3 minus x all over x. Which now we can simplify. It's equal to the limit, and I'm writing the limit every time. You guys need to as well. X squared divided by x gives us an x plus x divided by x is equal to 1. All divided by 3 divided by x is 3 over x minus x over x, which is equal to 1. Nice. Now, as we let x increase without bound, x plus 1 gets huge. In fact, it limits to a positive infinity. And as x gets really big, 3 divided by x becomes very small. That denominator is growing without bound, and the numerator is staying the same. So that's going to tend towards 0. So what we get is we get an infinity divided by negative 1, or a negative infinity for our answer. Like I said, there is a handy-dandy theorem that our book doesn't have written in it that makes it so you can one-shot this mini-boss by noticing something about it. And I will give you that theorem after you guys kind of work out with these. I want to see your guys' algebra where you are taking a look at the degree of the denominator and then multiplying by this 1 over x to the degree of the denominator and then simplifying. I am looking for these steps in your homework. Once I've seen you guys do all these steps, I'll give you an easier way to get out of these problems. We'll talk about it briefly soon. But for now, back to standard issue approach. Degree of denominator was 1. Multiply top and bottom by 1 over x to the 1. Simplify, evaluate limit. Put a box around your answer. Okay, the last thing we're doing, you can't see the graph, we're going to draw the graph, is we want to sketch. And let me make sure I'm still recording. We want to sketch y is equal to x minus 2 to the 4th x plus 1 cubed times x minus 1. We're going to be sketchy. We're going to be sketchy a lot during this semester. So we're going to be sketchy now. We want to graph this thing, sketch a graph, sketch that thing. Find its intercepts. Find intercepts and asymptotes. Intercepts, asymptotes, being sketchy. So, our intercepts. We'll start with our intercepts. By intercepts, we're talking about our roots. We're talking about our zeros. We're talking about where we either cross or touch the x-axis. All different ways of saying the same thing. It all depends on who you learned it from. Books kind of jump around. When we're trying to find our intercepts, what we're trying to do is we're trying to come up with the values of x that when we plug into this polynomial, this function has a value of 0. Well, it's already in factored form. We know that when x is equal to 2, or x is equal to negative 1, or x is equal to a positive 1, y is equal to 0. So we know our intercepts, and by looking at the degree of the factor, x minus 2 is of degree 4, it's an even degree, we know the graph is going to touch at x is equal to 2. It's going to touch the x-axis when x is equal to 2. X plus 1 is a factor of degree 3. Since it's of odd degree, we know x minus 1 is going to cross, the graph of this polynomial is going to cross the x-axis. It's going to cross at x is equal to negative 1. And finally, once again, x minus 1 is a factor of odd degree. It's of degree 1. Since it's of an odd degree, it's going to cross at x is equal to positive 1. If this was a refresher, if this was new, I have finally stammered long enough to remember the word multiplicity. Multiplicity. X is equal to 2 is a 0 of an even multiplicity. It's multiplicity 4. I believe I said degree a moment ago. It's an even multiplicity, so it touches. It's an odd multiplicity, so it crosses. It's an odd multiplicity, so it crosses. If you guys don't remember that, I would encourage you to look up the word multiplicity, see if it jogs any memories. I'm not just trying to kind of throw you something and run away. I'm not trying to hot potato an answer to you and dip out, in case that doesn't make sense. If you guys don't remember multiplicity, if you go through and read the wiki on multiplicity and it doesn't make any sense, shoot me an email and I'll get you all caught up. I'm trying to teach you, because you're never going to remember everything you get taught in a math class, and especially with calculus, this is probably your first multi-semester math course. You're going to be digging through your math book, your calc book in particular, back to chapter 1 stuff when you're in calc 2 and when you're in calc 3. So don't be afraid to look up something you don't know. When I went to high school, they said Wikipedia was a horrible, horrible resource, and once you finally get into doing more math, there's not too many people out there with malicious intent that want to rewrite a wiki page for a math topic. Check out the wiki for multiplicity if that part didn't make sense. After you do that, if you still don't get it, then shoot me an email and I'll get you all caught up. Okay. Touch, cross, cross. Intercepts are done. Asymptotes. We've got a polynomial. We've got a boring, a plain, a beautiful polynomial. It's not a rational function. That means we're not dividing by anything. The domain of polynomials is all real numbers. The reason why I say that is because that means we know we are not going to have a vertical asymptote. No vertical asymptote. We're not dividing. If you're not dividing, if there's no division, there's really no way for something to go to infinity in the middle of the graph. But we can talk about our horizontal asymptotes. Keep on dropping that I. For all I know, that could be how you not spell horizontal. I am all right at math. I am horrible at spelling. So, our horizontal asymptotes. Our horizontal asymptotes, this whole lecture has been about horizontal asymptotes mean we need to take limits as x goes off to infinity, or negative infinity. As x goes off to negative infinity. So this is a polynomial. A refresher, kind of about the same time you learned about multiplicity, you might remember that if you have a polynomial of even degree, your ends are going to go up to infinity on both sides. And actually that's a small box for that, because we've got 4 cases. So we'll say even, positive, even, negative, odd, positive, and odd, negative. for an even positive polynomial. And an example is something like y is equal to x to the fourth. It is going to increase at the ends. For an even polynomial that is negative, something like y is equal to negative x to the sixth plus x to the fourth minus 2x squared plus 5, something like that, is going to be a U shape, they might have said, but point down. There's a whole lot of stuff that can go on in the middle. We're just talking about end behavior. Sorry, I'm remembering the buzzwords from when I teach this lesson. And I saved myself no room right there. An odd yet positive, that's something like x cubed. That's going to go up on one side and down on the other. An odd but negative is the same but opposite. We'll go up over here and down over here. That's like negative x to the fifth or something like that. Okay, so this mini lecture on this over here, what degree is this polynomial? What degree is that polynomial? Well, we've got 4 x's right here, we've got 3 x's right here, and we've got another x right there. Without going through the process of multiplying this all together, we know that the degree of the highest term, we'll say the highest degree out of any term of this polynomial is going to be 8. We got 8 x's. So that means we know this thing is going to be of even degree, and we have 1 as a leading coefficient. 1's a positive number, so we know that this thing, I'm sorry, now I got my hands crossed. We know this thing is even and positive. So we know we're not going to have any horizontal asymptotes. We do know that the limit as x approaches infinity of this function is going to approach positive infinity. And similarly, as x goes to negative infinity, we're still going to approach positive infinity because we're even and we have a positive leading coefficient. So I'll write this here because we need those 5 pieces of information. This is just a sketch. If I wanted it perfect, I would tell you to graph. If I wanted it perfect, I would teach you guys, I would require you to use Desmos. If I wanted it perfect, I would teach you how to code in Python or MATLAB. And I would get it so you guys would tell your computer to give me a perfect graph. This is just a sketch. We're trying to figure out patterns, trends, whatever we can. We know we're going to touch at, well, let's put points we care about. We know we're going to touch at 2, and here's 2. And we know we're going to cross at -1, and we're going to cross at 1. We know that on the end, we're going to go up to positive infinity. We are going to go down. We're going to cross again at 1. We're going to touch at 2. And shoot off to positive infinity. Another one could have been something that looks like that. And do I have ink in that pen? I do not. I have access to maybe 3 colors. That might have ink in it. So there are a lot of different ways. I haven't used my fountain pen in a while. There are a lot of different ways you can draw these charts. When given the information in the problem, just knowing the x-intercepts isn't actually enough. Knowing the x-intercepts and the end behavior, I'll say, is not actually enough to recreate the graph. There are technically an infinite number of graphs you can draw.